So this is, I would say, joint work with a team. I would like to call the team the Hans, les Huns, who were in the 4th to the 6th century, because we have Alain, Sébastien, Gauvin, Valentin, Adrien, but there is a David inside. So, and now we have Teresa and Sébastien, maybe Gabel also. So this is really a joint work for a research that is really surprising. And I am almost at the end of my career. And this is probably the most beautiful result of all my career. So I will show you what we did. So, est-ce que ça avance là? Ah oui, ça avance. Oui, ouais, on va y aller tranquillement, voilà. Et puis on va y arriver. Hop. So, first of all, there is a link between graph theory and chemistry. You can represent molecules with a graph. So the atoms are the vertices of a graph, and the bonds in a molecule represented by edges. So we don't put parallel edges or loops in these graphs. And also what they call the valences of the atoms are called the degrees in the graph. So for example, hop, non, c'est pas ça que je voulais. On va y arriver. So for example, you have here a molecule that represents very straightforward as a graph. Okay. So chemical graph, it's a kind of graph that has some basic properties. First of all, it is simple. It means that you have no loop, you have no edge that links a vertex to a vertex. You have no parallel edges. And I will speak about this a little bit later. The maximum degree, depending on which category of chemists you are, its maximum degrees or at most 4 or at most 3. It depends on your view of chemistry. So I will speak about this later. But so you have a graph which is connected, simple, without parallel edges, and of maximum degree at most 3 or 4. Chemists are interested in defining indices that give you an idea of the value of a molecule. How good is a molecule, depending on what the chemists think. So they have invented topological indices, which are just numerical value. You give a molecule, and they compute a value. And they would like to know what is the best molecule according to the function that I give you. And among these topological indices, you have the degree-based topological indices. This means that the only thing they do, they put a weight on every bond, on every edge. And the weight depends only on the degrees of the endpoints. So if you have an edge that links vertex of degree 2 to a vertex of degree 3, this means that the weight depends on 2 and 3. That's it. So all edges having endpoints of degree 2 and 3 have the same weight. So you can define the weight. There are at least 50, if not 100, different degree-based topological indices that exist in the literature. The most famous example, the most famous example is a Renditch index. So if you have an edge with endpoint of degree I and j, they say that the value of this edge is 1 divided by the square root of I times j. This is just one example of index, which is the most famous that exists since 75, I think. So Renditch invented this function, this index. And so, for example, I will just give you an example. if you take this graph, you have 4 edges with degree n degrees 1 and 2. So degree 1, degree 2, degree 1, degree 2, degree 1, degree 2, degree 1, degree 2. So you have 4 such edges. You have only one edge, 1, 3, which is this one. And you have 4 edges of degree 1 and 4, and so on, and so on. And so you have different kind of edges, and then the Renditch index of this graph. So you have 4 times the 1, 2. So 1, 2 is 1 divided by the square root of 1 times 2. So it's 1 divided by square root of 2. So you have 4 such edges. So you make all the sum, and you get a value. And this is the Renditch index of this graph. So again, there are many different indices that exist in the literature. So where I am here. So the problem that chemists have, they say, I give you N, which is the number of atoms. I give you M, which is the number of bonds. So I would like a molecule with 13 atoms, 15 bonds. What is the best molecule according to my function I? I give you a function. I have my way of evaluating any molecule. I would like to know what is the best molecule according to some functions that I define. And I impose you how many atoms and how many bonds I want. So for example, if you take 13 and 15, as I said, and let's say that I don't take Albertson, it's easier to see perhaps the value of the Albertson index instead of Renditch. So the Albertson index, you take the degrees, it makes the absolute difference between the degrees. So if you have degree 2 and 3, then the value of this edge is 1. 2 minus 3, okay. So yeah, what is the best graph or best molecule which has 13 vertices, 15 bonds, and which minimizes this function? That's the question that chemists ask. And the answer here would be, there are 2 graphs. All these edges have value 0, because degree 2, degree 2, degree 2, degree 2. So 2 minus 2 is 0, 0, 0, 0, 0. 3 minus 3 is 0. Only 2 edges here have value 1, because it's degree 2 and degree 3, which means that for Albertson it's 1. So you have 2 such edges. And here also you have only 2 edges. And these are the only 2 graphs that minimize this function. So many, at least 100 papers have been written. So people give, this is my favorite function I write 20 pages and I tell you what is my best molecule. And we show you that you can throw all this to the garbage, because it's very easy questions that they ask here. We can now answer very easily to this kind of question. So, well, it's difficult to have 2 places where I have to go. Doesn't work anymore. Ah oui, pardon. En ligne. Désolé, je vais y arriver. C'est celui-là qui ne marche pas. Voilà. So, we started our research because of what claims that Gutmann said about these degree-based topological indices. He said, to use my expression, today there are too many such descriptors, at least 50, but I think 100. And we have to stop the proliferation of these topological indices, because they are not very different. They seem different, but there are too many of them. And so we made the first study in January of this year. This is also a cahier du GERAD with some co-authors from Belgium. We studied the 33 most famous degree-based topological indices, and we have shown that 14 of them have exactly the same optimal molecules. even if one is a logarithm of I don't know what, and the other one is a square root of they're totally different functions, but the optimal molecule is the same for 14 of them. And for 28 of the 33, we have only 5 families of graphs that are sufficient to characterize all optimal molecules. Strange. While the functions are totally different. So we said should be a reason for this. So why they all come to the same optimal molecule? So that's how we started our research. So let's speak about the problem mathematically. So since every edge which has endpoint of degree I and j have the same value, so if I have 2 and 3, so every edge with endpoints of degree 2 and 3 all have the same value. So I just call Mij the number of edges that have the endpoints of degree I and j. And if you have your favorite objective function, index, you just have a value for such an edge, Cij. If it is Rendich, it's 1 divided by the square root of I times j. If it is Albertson, it's the absolute difference between I and j. So whatever your function, you have a cost Cij associated with to such edges. And so what you want to do is just to minimize or maximize this function, which is the sum of Cij and Mij. Linear function. You want to optimize this over all possible chemical graphs with n atoms and m edges or m bonds. So this is your problem. So chemical graph, as I said, is a connected graph with maximum degree at most 3 or 4. So the main difficulty is how can we characterize, we would like linear constraints to characterize the chemical graphs with n atoms and m edges, since we have a linear function which is just the sum of Cij and Mij. So let's try to find a way to characterize chemical graphs with n atoms and m edges. And there is a way of doing it. This is a joint work with Pierre Hansen and Gilles Caporossi and some Mustafa Aouchiche. So this work started at GERAD. In 2017, we wrote a paper where we give a set of constraints that characterize exactly the chemical graphs. So don't look at the details. It looks like this. You have a set of constraints with the Mij inside. And if all these Mij satisfy these constraints, this means that you have a chemical graph with exactly the Mij edges with endpoints of degree I and j. So you can, so what we want to do is find Mij values. This means this will induce a graph. So if you know the Mij values, you will know which graph has these Mij values, but I want the graph to be chemical. If these Mij values satisfy this kind of constraint, don't look at the details, then you know that you have a chemical graph. So that's what they did, or what we did in 2017. And more than this, so perhaps first, so roughly speaking, this set of constraints I have shown you is not a set of linear constraints. But in the paper, it's explained how to linearize all these constraints. So you have to add 17, well, you have to have in total 17 variables. And then you have a set of linear constraints. And so the set of Mij integer values satisfy, if they satisfy this constraint, then you know that you have a chemical graph with exactly n atoms, n bonds, and this number of edges in your graph. So
I don't understand. Is Mij one of those variables?
yes, this is my variable.
So how come you are 17 and a half?
Because to linearize some constraints, so if I come back also
but
here.
What you mean is that you have
here you have something that is a square. And
my question is that
I had to add some other variables.
So you mean 17 artificial values?
No, I have the Mij variable plus some artificial ones.
But you have the Mijs too?
Yes, these are included in the 17.
Okay.
This is part of the 17, so I have added, you will see.
Well, the reason is that I is at most 4.
Yes, you have not so many, so you have M11, M12, M13, so you don't have so many. And but some constraints are non-linear, and there are several things that in order to put it in a linear way, you have to add, I would say, 14 variables so that everything is linear. But still, you have a linear problem. And once you have your linear problem, so in words, we know that a graph is a chemical graph with n atoms and n bonds if and only if the Mij values that you output, if they satisfy the set of constraints that is in this paper, you know that you have a chemical graph. So we just have to find the best. So our function now is minimize the sum of Cij, Mij with linear constraints, linear problem. It's a linear problem, integer problem. And also, what is very so what I summarize even here, optimizing a degree-based topological index reduces to solving an integer linear program with 17 variables. Okay, but what is important also in the paper is if you have found some Mij values, you say, yes, they satisfy a set of constraints. Okay, there is a chemical graph with these Mij values. There is a procedure in this paper in 2017 that show you how to build a graph, which not only you know that there is a graph, but it's very easy to obtain a graph that satisfies it.
So in all graphs?
No, so there are too many. So sometimes you can have with the same Mij values, you can have an exponential number of graphs. But chemists, they just want to know the optimal value and an example of a molecule, but the number of molecules that satisfy this can be very big. So I will use it later. So let's make a picture of what we did in 2017, and I will come to what we did now with the new research. So it's in dimension 17. I've shown you a picture. Assume that you are in dimension 2. So you have the red points are the chemical graphs. The white points are integer points which do not correspond to chemical graphs. So some Mij values which are integers, but they do not correspond to chemical graphs. Only the red one. And the constraints we have given give you a convex hole. And if you are in the gray part, you know if we have an integer solution in the gray part, it's a chemical graph. If you are outside of this gray zone, an integer solution is not a chemical graph. So the red points correspond to chemical graphs, and the black points are the extreme points of this convex hole. So what you want to do is to optimize a linear function on this set. So with an image, if you have a linear function like the one that you see here, then the optimal solution would be, if you maximize or minimize, it depends, it will be one of these 2 points. So you have to work a little bit. And my question is now, can we do better? yes, of course, you can do better by considering the integer hull of these chemical graphs. So the picture is coming now. If you take the integer hull, so the convex hull of all integer points, so you get this gray region, which is smaller. But what makes the idea very interesting is that if you have a linear function, then you can forget about the integrality constraints, because the optimal solution of a linear program is an extreme point, and an extreme point of this convex hull is an integer point. So what we would like to know is what is this set of red constraints instead of the set of black constraints. And this is what we did with my team, les 1, Sébastien, Gauvin, Valentin, Adrien, and David. He's a good friend of mine, David. He was the GERAD, so sometimes he spent at least 1 or 2 years here. So that's what I want to focus now. That's the new research we did this last month. So there are two definitions of what is a chemical graph, as I said. So I am not a chemist. Some regard look at molecules, the skeletons of saturated hydrocarbons, such as alkanes. Gerhardsen would have explained all this. He had a background in chemistry, and he could explain this. I don't understand anything. For me, it's just maximum degree is at most 4. And the other category of chemists, they say, no. They are interested in unsaturated conjugated systems such as alkanes, polyenes, benzenoids, fluorines, for which the molecules have maximum degree at most 3. So we have two types. So we decided since 3 is smaller than 4, let's start with 3. The problem is probably easier. So from now on, I will only focus on maximum degree at most 3. So I cannot have any vertex of degree 4 or more in my graph. So let's make a picture, a comparison of the polytopes. Here I am. Again, it's a view just to make you understand what we did. This is what we did with Gerhardsen and the co-authors. This example, which is in 2 dimensions, but we don't work in 2 dimensions, you have only 14 black points around, which are extreme points of the polyhedron. Here in this example, we have only 6, which are all integer points. So what if we take, in reality, the real polyhedron that we get? Let's say you want a chemical tree, a graph that is a tree. You have 14 vertices and only 13 edges, and maximum degree at most 3. So what do you get? So as I said, they have 17 variables. As we will see, we have only 3 variables. Our problem has only 3 variables and not 17. I will come at this later. So we work with less variables. They have 27 constraints. We have 10 constraints. But what is very interesting is that with this model, you have 11,648 extreme points. 99%, if not 100% of them, non-integers. So you have to work to find the optimum integer, best optimum, which is an integer. In our case, we have only 12 extreme points, and they are all integers. So much easier, 11,000, 12. So, okay, but this is a simple example, of course. So my question, so In this case, it would reduce what is the best of the. You have only 12 possibilities to be the optimum. Ah oui, merci. J'avance en ligne aussi.
C'est pour ça avec le domaine.
Voilà, c'est difficile de se coordonner. Oui, so, in this case, I would have reduced the problem to know what is the best point among 12. My question is, let's imagine a function f of nm, which given a number n of atoms, given a number m of edges, gives you the number of extreme points of the integer convex hull. So we had only 12 in our case, but it depends on n and m. So my question is, how does f and m vary if you change n and m? I want now a molecule with 1,000 atoms and 1,348 edges, what is the number of extreme points of the polyhedron? That's my question. Is it linearly, quadratically? Those who know the answer, please don't give the answer. And those who don't know, you can try to guess. So how do you know, how do you think that the number of extreme points will vary according to n and m? Any guess? That's a surprise that I will give you, that I could not imagine the answer. It's constant. Even if I want a molecule with 10 millions of atoms, the number of extreme points is never larger than 16. Never larger than, you never have more than 16 possible optimal values. Whatever the number of atoms and bonds. I said it's surprising. For me, it's just unbelievable. And I will show you how we came to this conclusion. So just keep in mind that never larger than 16. So how did we come to this? So we made some mathematics. So since we have maximum degree at most 3, this means that we have only 6 variables. M11, M12, M13, M22, M23, and M33. But one of them, M11, is not interesting because if you have M11 larger than 1, so if you have an edge linking a vertex of degree 1 to a vertex of degree 1, this is just an edge. Since my graph is connected, I have only 2 vertices, so I'm not interested. So I suppose my graph has at least 3 vertices, and so M11 is not interesting, it's always 0. So I have only 5 variables. These are my 5 variables, okay? This is starting point. And I can easily write what is the total number of edges. This is the total number of these numbers. So I have I have 10 like this, 15 like this, and so on. So the number of edges is like this. And it's not difficult. It takes you 1 line, but I will not give you the proof here. The number of vertices also can easily be computed according to how many edges of this kind. And you can know how many vertices you have according to these Mij values. So I can write M and M with these 5 variables. And since we are supposing that M and N are given, so I can just choose 3 variables, only 3 of them, and then the 2 others can be deduced by these 2 equations. So that's why we work with only 3 variables. And we have decided, so we need only 3. And we have decided to use only M12, M13, and M33. So the 2 here, M22 and M23, you can compute their values once you know the others, and knowing n and m, you can easily get the others. So I have a problem with three variables. So even I can represent it. It's a three-dimensional space. I want to optimize a linear function in a three-dimensional space in a convex hole of all chemical graphs. That's what we want to do. So, of course, the objective function, I will come to this also later. So this is the objective function. Since I don't want M22 and M23, I can rewrite M22 and M23 and get new coefficients by three variables. These coefficients are easily obtained from the others. So this is just algebra. Just to give you an example because I will use it later. If you take Albertson index, so I have to compute C prime 1, 2, C prime 1, 3, C prime. So for example, this one. So for Albertson, it's the absolute value of the difference. So this is 1 minus 4 times 0 plus 3 times 1. This is 4. So you have a 4 times M12. And this is 2 minus 0 plus 2. This is 4 also. So you have a 4 here. And this is 0 minus 2 plus 0. This is minus 2 for here. So it's very easy. So if you want Albertson, so my function, if I want to optimize the Albertson index, I just have to optimize 4 times M12 plus 4 times M13 minus 2 times M33. This is for Albertson. For any other index, you get a very simple formula and you know what is your linear function. So we call a triplet of these values realizable if there is a chemical graph with n atoms, m bonds, and the right number of edges of each type. So you should have exactly M12 edges limiting vertices of 1 and 2. Some triplets are not, if they are not integers, they do not correspond to anything. If they are integers, I would like that a chemical graph exists. So what we do is just a convex hole of all realizable points. That's our convex hole that we are looking for. So we call it PNM. If I give you N and M, you get a set of realizable points and you make the convex hole of all these points. And this is a region we are interested in. So we're interested in looking at the extreme points of this polytope. So and here, once I know this polytope, so the optimum, as I said, is always, to go here also, it's always one of the extreme, the optimum value. They don't have to put integrality constraints. It will be one of the extreme points, which is integer. So my question is, what are the extreme points of these polytopes? So what we did, we defined 21 inequalities involving these MIG values, and we defined 21, let's say, chemical graphs, 21 points which are realizable. Just 21. For example, one of these 21 inequalities is 2 times M12 plus 1 times M13 minus M33 should be at least equal to 3 times N minus 3 times M minus plus 1. This is one inequality. It's not always valid. It's valid under some conditions that depends only on N and M. So for example, this one is valid if your graph is not unicycle, the number of edges is not equal to the number of vertices, and if your number of vertices is odd. Otherwise, it's not a valid inequality. So we have 21 inequalities with conditions. And so every inequality has its condition. So this is only possible if n is odd. This is only possible if m modulo 3 is equal to 2. This gives you a partition of, since you have only 21 inequalities, of the space of all pairs n and m into, sometimes this inequality is valid, sometimes it's not. So we get 96 different groups, each having its set of valid inequalities. So in each group, you have a subset of the 21 inequalities that is valid. Just valid. I know that they are valid in this case. So any pair of n and m is included in one of these 96 groups. So, for example, you have one of these groups that says it's only valid if n is odd, m is a multiple of 3, and the m is not too small, at least equal to 6 times n divided by 5, and not too large. It's at most 3 times n minus 1 divided by 2 minus 2. This is one of these 96 groups. And in this group, you have a subset of these 21 inequalities. And so each of these 96 polytopes, because you have just valid inequalities, is just defined by a subset of these 21 inequalities. And what we have shown, okay, it's perhaps too big. So there are valid inequalities, but perhaps they contain too much. But we have shown that the extreme points of this convex hull for each of these polytopes is always a subset of these 21 realizable points. Everyone has extreme point only a subset of these 21 realizable points. So this means that we covered exactly, so each polytope doesn't contain too much. You have no extreme point outside. So every extreme point is a realizable point. So that's what we got. And our main result, which is really surprising, so whatever n and m, the polytope, one of these 96 cases, has never more than 10 valid inequalities, never more. So we have divided, and among the 21, you had never more than 10 of them active, the 10 facets. And among the 21 realizable points, you have only 16 of them maximum. Sometimes you have much fewer, so 16 points. And all of these points are realizable. So these are the extreme points we were looking for. So that's really surprising. Even if n is equal to 1 million, we have only 16 points maximum. So for example, take the same example as before. If n is odd, m is a multiple of 3, and n is not too small and not too big, then you have much less than 10 facets and 16 extreme points. You have 5 facets only. So very easy. M12 should be larger or equal to 0. M13 should be larger or equal to 0. It cannot be negative. You would say, and what about M33? But it's because of this, it's implied also that M33 cannot be smaller than 0. So you have 3 additional constraints. And with these 5 constraints, only 5 constraints, you have a polytope that contains only 6 extreme points, which I give you here the value of these 6 extreme points. So this is one case. So let's say that a chemist comes now and says, I would like to know what is the best molecule with 15 atoms, 18 bonds with the Albertson index. What's the best? I said, very simple. First of all, n is odd, okay. M is a multiple of 3, and you can check that this is okay. So I am in this is one of the 96 polytopes. To know which of the polytopes this is a partition, it's very easy to, so this one 15, 18 become to this position. So I know the extreme points there are only possibilities. Your optimal molecule you are looking for is one of them. So you gave me 15 and 18, so I can compute the value, replace n by 15, and I replace m by 18. And so, for example, 5 times 18, which is 90 minus 6 times 15, which is 90, you get 0. So 0, 0, 0. So I compute the value of this point. So, easy. Then I look at this function. Then you remember for Albertson index, this is function that I want to optimize. So I compute this value. So 4 times 0 plus 4 times 0 minus 2 times 0 is 0. Second, 4 times 0 plus 4 times 4 minus 2 times 12, which is minus 8. So it's very easy to compute. Maximum 0, minimum minus 16. Finished. Instead of having 20 pages of computations, you have many papers in journals. They try to find the best molecule. I say, it's only one of these 6. And as I said, we have a procedure from the paper with Pierre and Gilles and Mustafa and co-authors. If you give me a triplet, I can give you a graph. Very easy, a polynomial procedure. So here is a graph, one graph. There are many others, but this is one example of a graph that maximizes Albertson index, and you have 2 that minimize. Here is 008, and this is the 1010. So you have no edge 1, 2, you have no edge 1, 3, you have 8 edges 3, 3, which are the 1, 2, 3, 4, 5, 6, 7, 8, and the rest is 2, 3, which is not recorded here. Okay. So very easy to optimize. And more than this, if I take now this graph, for example, it has also 15 vertices. It has also 18 edges. You can check. This point is 109. I have 1 edge, 1, 2. I have no edge, 1, 3. And I have 9 edges, 3, 3. It's 109. It's not one of these points. So whatever the chemist has in mind, if we would like this molecule to be optimal, it is impossible. He cannot invent a topological index for which this graph is optimal. It's not an extreme point of the polyhedra. It will never be an optimal molecule. Never. There are only 6 possibilities with 15 vertices and 18 bonds. So we can say, don't try to make this molecule your best molecule. It will never be, unless you have a non-degree-based topological index. Otherwise, it cannot be. So this one doesn't optimize any degree-based topological index, and even these topological indices that have not yet been considered. Perhaps in 10 years, you will say they will find some. No, it's impossible. It will never be an optimal. So in summary, what we have done now is to give a complete polyhedral description of chemical graphs with really the integral convex hull for maximum degree at most 3. Of course, we have to go to maximum degree at most 4. And so we have to add 4 variables, M1, 4, M2, 4, M3, 4, and M4, 4. So instead of having 3 variables, we will have 7. So we will work in dimension 7. This is what I am doing now with Teresa. She's working here with me and Sébastien Ledigabel. So we are working, and of course, all the team in Belgium, all my co-authors, and David Schindel, who is in Switzerland. So we made some tests. just to have an idea. So we will have to work in 7-dimensional space. It seems that what we tried, the most difficult case, I would say, with the largest possible number of extreme points, is around 400 points. It's not thousands and thousands. It seems that we will never have, we had 16 as maximum for degree 3. We have probably 400 or something, a little bit more for maximum degree 4, which is still, so you record all these points and then you compute the value of your molecule and you test which one is the best among these 400 and you get the best one. So we are trying to reproduce the same kind of results for maximum degree 4. So that's what we are doing now in a team that has 8 participants, and it can go even more, perhaps. So we will have to work harder with Teresa and Sébastien, and that's it. Unless you want me, I don't know, can I share my screen? They will see if I go to internet. No, because we okay. I
do that on the 2 computers.
Okay, so I just tell you if you are interested, we have developed a website which is called Chemical for the convex hull. So H-U-L-L at the end, Chemical. And so if you go there, you give your number of vertices, you give your number of edges, you give your favorite function that computes your index. You click and you get your molecule, which is drawn on the computer and show you what is the best molecule. So instead of writing papers, so since the 70s, they've written hundreds of papers trying to find the best molecule. So now they just can go on the website and see what is the best molecule. And we even give the reason with the facets, the polyhedral description and everything. So future work for next year, I will again speak on, perhaps Teresa will speak about our results on maximum degree 4 next year. So thank you for your attention.